As you guys can hear, I am very excited to host this webinar since it is about one of the hottest topics in our industry. We will talk about AES67, guys. Is it going to change the future of audio networking? And how will it affect our daily business? And of course, and very, very important, you guys can see it maybe, it's an Extremer M400, my personal favorite product here at Barix. How can I connect my device with AES67? I have the pleasure to work very closely with our presenter today. He is the expert if you want to gain inside knowledge about AES67. Thanks for being the presenter today, and may I hand over to our product manager at Barix, Mr. Davide Nossa.
As Patrick, I am also super excited about this webinar, AES67. It is one of the hottest topics nowadays, even if it has been around since a few years now. It is seeing mass adoptions only recently by many manufacturers. And in this webinar, our goal is to give you some theory, some background on the standard, on the technical standard, on the definitions of the standards, on the requirements, and how we made it possible to have it available on our IP audio client product line. As you can see, I have with me on the table an IP former, 6 watt on 4 ohms load IP decoding amplifier. Then I have an Extremer M400, which has a line level output, as you saw, RCA connected on the backside of Patrick's unit. And then we have also this new, it is not shipping yet. This is the Extremer MPA400. It's the same as the IP former, but with a more capable powered output. This is able to drive up to 40 watts loudspeakers on a 8 ohm load. So this is not shipping yet, as I said, but we hope to be able to ship it soon enough. I have it here because he is also running the IP audio client, so it will be possible to drive an AES to make it compatible with AES67 compliant devices. And also I have here on the desk a Dante AV-IO device. Many of you probably know about this little tiny powerful device. This is the encoder that we will use for our demo right after. So without any further ado, let's go into the presentation and we can see what topics exactly we will cover during this presentation. So give me 1 second here. Perfect. So these are the topics. We will go through some history on the AES67, why the standard is there, why is existing. We will demystify the building blocks of every networked audio solution. So having this in place, the theory behind, we can understand why AES67 was needed in the market. Then we will move forward into some practical examples, analyzing the principles on which AES67 is based. This is very useful for system configuration approach. And we will move forward looking at our implementation of AES67 into IP audio client and how to connect the IP audio client with a Dante AV-IO device. We will see it on a real demonstration. And the next steps, so what will be the future for AES67? At the end, we will address all your questions, as Patrick already mentioned. So let's start. Let's start by saying what was there before AES67. In the first decade of the years 2000, many different audio over IP solutions were emerging. And the goal was common for all of them. It was for transporting audio over what normally were the scope of IT departments, thus IP networks. The most famous audio over IP solutions, you can see them on the screen. And we can split them into 2 main categories. On one hand, we have the installed sound, and on the other hand, we had the broadcast transportation. So these manufacturers, these technology providers, were developing, each one of them, solutions independently. So they were developing audio over IP complete solutions, and this is an important definition, but they were resulting in being isolated systems. As you can see in the slide, they were like isolated clouds. Each one of these manufacturers and implementers were working on its own personal implementation. So while audio over IP solutions should allow connectivity at easy, this became a bit complex to handle. For example, if you had being maybe a consultant and you wanted to connect a Dante microphone to a Ravenna-based mixing desk to a QLAN loudspeaker, this was very difficult to achieve and very hard to maintain over time. It was clearly missing a standard that allowed those solutions to interoperate between each other. In fact, there were many challenges, and those challenges were not affecting only consultants, as I said, but all the parties involved in a decision-making process to reach a final decision to build a system. On one hand, consultants had to choose from a subset of products supporting the same solution, or accept a compromise when connecting between different ones, which means, should I go back into the analog domain to connect my devices? Well, this sucks, let me tell you, because you have to go back, convert and reconvert to go digital. Yeah, it's a compromise, a big one, but it was an easy one actually to implement. System integrators were faced with an increased complexity of the systems, and the maintenance over time was becoming an issue, as each one of those systems were maturing. So adding new feature, the system integrator had to be trained on different solutions. It was a kind of a waste of time. Same applies on the manufacturer side. So the manufacturers had to think about licensing, for example, licensing a technology, hoping that this would be supported over time. Furthermore, it was a waste of time on implementing different networked audio solutions, not focusing on the actual product features effectively. Again, it was clearly missing a standard. And at this point, I might know what you can think. It was so easy in the old good days of the analog audio. We had this beautiful mass of copper that was simple as point-to-point connection. An XLR here corresponds to an XLR on the other side. Yeah, but yeah, a lot of waste of copper. Fortunately, AES67 arrived and saved us. And going forward, the meaning, the definition of AES67 is exactly this. So if you look at the standard itself, this is the title of the standard, is a technical standard for high performance streaming audio over IP interoperability, where interoperability is the key term to keep in mind in this presentation. AES67 is a technical standard and is a conglomerate of multiple technologies and protocols. It was released back in 2013, and after that, it saw two minor updates, one in 2015 to clarify some patent issues, and the other one in 2018, where it was added that were some annex and more recommendations, and the performance test compliance statement was also added. But moving forward, why we truly needed AES67? So why we needed this standard to allow interoperability? So why the different solutions were not compatible between each other? Let's move forward and analyze the building blocks of a networked audio solution. So let's dive a bit more into the details of the main requirements. And what you see on the screen now, those are basically the common building blocks of a network audio solution when it is implemented. So these are from A to Z, everything that is required to have an encoding device sending a stream over the network and on the receiving device being able to decode it. These are the building blocks. This is useful to understand in order to better grasp the AES67 existence. Is a model, this one that we are seeing, and it is being used across all the different solution providers that we just analyzed. And if we go into each one of these building blocks, we can see clearly what is about. We have the device control, which includes the features to control and monitor. For example, editing the channel names, the input levels, you want to configure your sampling rate, retrieve the health status of the device, etc. Is something that is happening, for example, on our Barix devices when you connect to the HTTP web interface. The connection management block, which includes sub-blocks for discovery, connection management, and session description. But overall, the connection management block is where the devices are exposing the streams identified in the network. So away from the device, from the system, from the solution, to put your devices into the network, connect them, and have them being capable of recognizing each other using a discovery protocol. Once they are connected between each other, they have to allow the transport of the session information, which include the media clock information, the unicast or multicast stream, where the decoding device has to get it to allow the transmission and the reception of the stream. So it's all about connection. Then a complete network audio solution have to include the transport. This is the core of the solution itself. So it's required to have a way to move the audio samples in a synchronous way through the network. The transport block is where you have basically the specifications for the protocol to be used for moving the samples, how to configure the quality of service of the network in a way that the equipment in the middle knows how to prioritize it. And then we have the encoding and streaming. So which formats those samples must support to be compatible between one end to the other. So which encoding formats should be used. Last but not least, actually, this is one of the most important ones as well. To move samples synchronized in a network, we need timing definitions. And in this block is where we have the definition of the technologies to be used, or of the protocols to be used to distribute the clock through the network, and which media clock should be supported. So what protocol to transport the clock and what sampling frequency we have to use. This is the definition of the timing block of a networked audio solution. For example, if we want to see these blocks, this model applied to one real solution, we can take Dante from Odinate. And let me clarify, first of all, this is Dante before 2015, before the update to the Brooklyn 2 firmware. So when AES67 mode into Dante device was not yet there. We can clearly see that there are many proprietary blocks here. So for control and monitoring, discovery, connection management, and session description. And then we have some blocks that are not proprietary, but they are relying on existing standards, existing standard protocols. Beside the transport that was proprietary as well before 2015, we have a standard quality of service management relying on differentiated services code points, the encoding and streaming, well, this is normal digital audio transferred over the network with 16 up to 32 bits, with at least 4 channels and more, in this case for Dante. Synchronization using PTP, this is the version 1 of the PTP. And then the media clock from 44.1 up to 192 kilohertz. So we can see that a networked audio solution is nothing but a collection of standard or proprietary protocols. When they are combined, you have devices able to communicate and share data. So This view is also useful to make use of the right terminology. A protocol is not a complete solution. So it is not correct when we say Dante protocol. Dante itself is not a protocol. Dante is a complete solution, a set of multiple protocols that when combined, they allow communication from A to B. And now we can see all the different solutions, network complete audio solutions that we exposed in the first slide, and which protocols and definitions are used for each one of them. I'll give you 1 second to analyze the blocks, and then we can understand why this is not compatible. So as you can see, there are so many different from proprietary to standard options used across all the different manufacturers that leads to incompatibility. This is the reason why the different solutions were hard to connect between each other, because they were not talking the same language for each one of these blocks. So despite these solutions are all based on IP technologies, they were using different protocols to satisfy the base requirements of a network audio solution. And this is now the scope of AES67 and why it was born. AES67 was created to identify the common items, technologies, protocols used by the main audio over IP solution providers, and to provide a guideline to make them interoperable. So to allow connections in between each one of those at easy. In fact, once commonalities between all these solution providers are found, it becomes easy to reach audio interoperability between different solutions featuring different network technologies, such as Dante, Ravenna, QLAN, Livewire, and others. And one thing that has to be clear is that AES67 itself was not born to be a complete solution. In fact, AES67, if you notice from this picture, is not including control and discovery. So the first two small blocks, they are not included in the standard. Despite AES67 makes recommendation on how to do discovery, it is not saying the protocol, the implementation must support this protocol in order to discover other devices. For this reason, AES67 is not competing with none of the other solutions, but it complements them by providing a method to share audio over the network. In fact, what happened after the standard was released in 2013, some of these solution providers was adding a so-called AES67 mode, like a new feature implementation, which would allow the possibility to reach the interoperability with other solutions where AES67 was supported. And moving forward, let's go and see what are the actual protocols and technologies specified in AES67. Again, you can see that AES67 is only is only defining into the standard protocols and formats from the connection management block up to the media clock, leaving out the discovery. And if you read the standard, it is clearly stated that devices are not required to implement discovery services. Devices may implement one or more discovery services, including Bonjour, SAP, and others. So it's a bit fuzzy in this definition, but the mean is not required. Devices may implement, it says. So it's up to the manufacturer, to the implementation provider to decide which protocol to use for discovery. And discovery, remember, is the building block that allows one device connected to the network to automatically identify a stream from another device in the network. So for the discovery is clear. For the connection management, we have two definitions that are basically combined, let's say, with the session description. So let's talk about the connection management and the session description. These two blocks are used basically to specify the critical information about each stream, including the network addressing, the encoding format, and the origination information. So what devices is originating the stream in the network. And AES67 says for unicast connection, you have to use SIP, which is the session initiation protocol. For multicast session, you have to use IGMP. Again, this is quite related to the discovery protocol again, because in the discovery suggestion that AES67 makes, it says it may implement one across Bonjour, SAP, and other. Bonjour is based on MDNS, DNSSD, and SAP is a session announcement protocol. Both of them are relying on multicast, thus IGMP configuration in the network. I remember that IGMP stands for Internet Group Management Protocol, and it is available in managed switch to be configured in order to allow an easy traffic management option. Moving forward, the transport block defines the RTP to be used for moving samples over the IP-based network, so over IPv4 networks. The default ports used for the RTP are the default ones that mandates the standard, or 5004 and 5005 if also our RTCP is being used by the implementation. The quality of service, it's relying on the differentiated services code point values. We already mentioned this before. And what is this? It says you implementer have to tag your IP packets according to the standard. And AES67 specifies 3 classifications from the most important one to the lowest important one for PTP packets, RTP packets, and the other type of traffic. We will see more on this in a later slide, where we have a table describing exactly how this is implemented. The encoding and streaming. The encoding and streaming is basically describing the means in which audio is sampled, is digitized, and formatted into the sequence of packets that forms a stream. AES67 requires a 48 kilohertz sample rate, as you can see also from the media clock, even if it leaves options for use also 44.1 and 96 kilohertz. And the payload for 48 kilohertz must be linear 16 bits or linear 24. The packet time, which you can see basically in the encoding and streaming always, we can see linear 1624, 48,000 samples per second. And then we can have 1 millisecond. 1 millisecond describes the packet time. And what is the packet time? The packet time, it is the duration expressed in milliseconds of a packet. Thus, when we know about the sample frequency, we can calculate the number of packets that goes into each packet. Sorry, the number of samples that goes into each packet. To reach the maximum interoperability, AES67 says that you have to use 1 millisecond packet time, where each packet, if you make the math, includes 48 samples of audio data. The synchronization. Synchronization is achieved using PTP, or Precision Time Protocol. We will see more on this topic in a minute in the next slide. So I will leave this description right after. And the media clock is nothing but the sampling frequency that has to be used for digitizing the samples. So how many samples per second my encoder has to digitalize. Okay. Now that we, let's say, analyzed the standard. So this is really, this is going into the details of the standard. It is published, by the way, so you can see more on the topic if you go on the internet. But we can see, we just defined basically all the building blocks that AES67 describes into the technical standard. Now, let's see from the system configuration perspective, what are the most important principles that we should take into account when we are building a system. AES67, one of the most important things that we have to say is that is not telling the vendors how to implement the protocols and the technologies defined in the standard. For this reason, the solutions on the market are different from one another. Just think about the discovery protocol that is used. We have Dante, for example, that is using, after 2015, Dante implemented SAP as the discovery protocol. On the other hand, Ravenna is not using SAP. It has a software that allows the translation from SAP to MDNS, DNSSD, or Bonjour. So this is what Ravenna is using for the discovery. For this reason, it's important to consider when you want to make devices interoperate between each other, it is important to check the feature capabilities. When a device is said to be AES67 compliant, it doesn't mean that out of the box is capable to connect automatically with another device. You may want to check the feature description. But the main principles, so the 4 principles of AES67 when you are configuring a system are described in this slide. From top to bottom, synchronization, multicast configuration, quality of service, and session information. This is an excerpt from your practical guide to AES67. It is published on the Ravenna website. They were actually Ravenna. If you also look at the previous slides, let me go back a second so I can show you. So if you look at Ravenna, you notice that there is no proprietary protocol being used by them. This is why when AES67 was released, Ravenna was capable of transporting audio right out of the box using AES67, because they were already basing their implementation on standard protocols with an extended, actually, set of options. If you take a look, for example, at the sampling frequency that Ravenna devices are capable of, they are going up to 384 kilohertz, which is much out of the AES67 definition, but they support, of course, all the subset of what AES67 mandates. This is true also for the channel count capabilities, for all the rest. So basically, Ravenna, since AES67 doesn't mandate the discovery and the connection management and how to transport the SDP, which instead is part of the definition of AES67. AES67 says you have to use an SDP, which is the session description protocol, but it doesn't say how to transfer this SDP from one device to the other. But Ravenna implemented this connection management using standard protocols, or RTSP, and in combination with MDNS, DNS-SD, which is Bonjour, and SIP when it comes to unicast connections from one device to the other. But let's go back into the slide where we arrived before. This was a parenthesis about Ravenna, since I took the information you are seeing now from the excerpt, your practical guide to AES67. It's a very nice one. When you have to build a system, you may want to read it. But let's see each one of these principles, how it works, and what we have to consider being system administrators when we are setting up our devices to communicate. Synchronization. So we saw that AES67 says you have to use PTP, which is the standard created by the IEEE Alliance. And it's the 1588-2008, so PTP v2. The precision time protocol provides basically a way to keep the endpoints in your network synchronized to a reference clock. PTP basically includes what is known as a BMCA algorithm, best master clock algorithm. This ensures that the best available master clock is elected among the device in a system. So when you have your devices connected, there is one device and one only that can act as a master clock, as a reference clock or wall clock in the PTP world, that basically sends the PTP, the information on the time, to all the endpoints. In this way, the endpoints are capable to keep synchronization between each other. So to keep the media clock, the sampling frequency accurate when it is transported using the SDP file over the network. So from one end to the other, the SDP is provided, and the SDP contains information about the media clock being used. And since both devices, in this case two, let's say, are connected to the reference clock, they have a very accurate timing in handling these samples. That's why the transport is synchronized in AES67 environment. And this is very important to reach high performances, where high performances means real-time, low latency transmission. The accuracy using PTP, it's really incredible, even if you are not using non-PTP aware switches. So PTP is not implemented at the hardware level, or not in the switch, sorry. In the switch is not implemented PTP, you can reach a single-digit microsecond accuracy. If you deploy PTP-aware switches, which are a bit more expensive, you can reach an even greater accuracy for the clock distribution. So the devices will be fully synchronized. Is important, this will bring us to the next slide. PTP works on top of multicast communication. And PTP is divided into domains. The default one that is described in the AES67 standard is domain 0, which says that the reference clock should advertise the PTP messages on the address 224.0.1.129 on ports 319 or 3120. In knowing this information, devices supporting PTP, the standard, knows where to look for in the network to retrieve the PTP information and keep this updated over time as the connection is open. The second the second principles of AES67 is the multicast configuration. Multicast is essential for AES67. It's not only used by PTP, as we just saw, but also for audio and for the discovery mainly. It's quite rare to see devices using unicast for the discovery, even if it's possible using SIP, as we noticed. But mainly we have multicast discovery protocols being deployed into an AES67 capable system. And also for audio, as I said. It is recommended to use multicast-based protocols for the connection management and the stream discovery. And nowadays, any commercial off-the-shelf, so COTS switch, are supporting the multicast. But pay attention that only the managed switches are providing effective multicast management. Why is important that you use the managed switches? To avoid network flooding. And let me tell you, if you use an unmanaged switch, this will forward any incoming multicast packet to all the switch ports. This is bad because it could result in a network flood, causing a total network lockup. Since AES67 highly relies on multicast for the audio transport, and if you think if we have one packet every 1 millisecond, you have 1,000 packets going into a multicast address every 1 second. 1,000 packets is a lot. So it's easy if you don't have a managed switch, an unmanaged one, if you don't have the switch capable of handling very well the multicast traffic to have a network lockup. Well, it's not very easy. Nowadays, I know that switches are basically very smart and you can rely on them. I also tried and tested many different unmanaged switches, and they work out of the box.
Davide, can I just interrupt you for a second? I think
Yes.
Daniel raised his hand. I think he has a question to this slide. Maybe we can let him ask the question.
Okay, yeah, sure. Can you read it for me, please, Patrick? Because I don't have the chat or the Q&A open.
I think he just raised his hand, if I'm right.
Okay, so let's wait for Daniel to...
Yeah, Daniel, if you want, you can pose your question right now. Or maybe he just pressed the button. Oh, sorry, error button. Sorry, Davide, for interrupting. You can continue.
Okay, well, maybe you can also write the questions down and we can address them at the end. If I have to go back into some slides, I can definitely do that. So moving forward, managed switches normally are supporting what is known as IGMP snooping configuration. And only in this IGMP snooping, when this is enabled, only the multicast packets that have been registered through IGMP are forwarded to their designated ports. Another important benefit of multicast is that it offers scalability out of the box, because any multicast flow is only sent once by a particular sender into the network. If more than one receiver requests the same flow, the network switches will do nothing but clone the packets as required. So with IGMP support, the network is largely optimized. This is why it is important. The quality of service. As we noticed in the previous slide, AES67 says that we should use differentiated services for handling the quality of service. And AES67 truly defines which values into each code point of the differentiated services we should tag our IP packets. And it says for PTP packets, you have to use this tag. For RTP packets, you have to use this tag. And for the rest of the packets, you have to use this other tag. This is why it is important to have the possibility using managed switches to configure the quality of service using the SCP values. How the SCP works. The SCP says you have 64 different values and you have to tell the switch which one is the most important, which ones are the most important. So you can also assign the same priority to multiple type of values. You can see this as a boarding pass priority when you go to the airport. There are first class users that are going first, business class second, and economy class that are going last. But be aware, and this will be very much clear in the next slide, different implementations of AES67 might provide different DSCP values. So it's important to know which values each implementation are truly using, because AES67 says you have to use these DSCP values, but then we have a manufacturer that is not doing that, is not tagging IP packets following the standard, but they are saying that they are AES67 compatible. So if we go into the table here, we can see that this is what the standard mandates. We can see that the quality of service DSCP tags recommended are for the PTP used for the clock synchronization. The DSCP code is the one for expedite forwarding, and the number is 46. So in my switch configuration, I will have to look for this code or this value, depending on the switch you're using, and say this packets with this tag has to be more important. So you are giving them more priority. Then we have the RTP, which is right after, so the audio transportation, which is using the DSCP value 34 or AF41 as a DSCP code. And for all the other traffic, this is best effort. So it has the lowest priority. But let's see what, for example, Dante uses. So when you combine a system like our IP audio client with our Dante device, Dante, if you look up at the documentation that they provide, is not using the default, let's say the standard values that are described into the AES67 standard, but they are using different values for the PTP. And this is the SCP code CS7 with the number 56. So I will have to give more priority to the tag 56 into my switch configuration when I have a Dante encoding device in the network, sending this information to my endpoints. For the RTP, I have the value 46. Then we have a proprietary tag here that is using the CS1 and has value of 8. So to the number 8, I have to give the third priority tag. And we have all the other traffic, which is best effort. Moving forward, the last principle that is important is the session information. The session information is described fully in the SDP, which is what AES67 mandates to be used to describe the session. And what is inside of this SDP file? It contains the multicast address of the stream, the encoding format, and the packet setup. So the bits per sample, the sampling frequency, the number of channels in a stream, the number of samples in a packet, and so on. And the last one is the relationship to the reference time. So we have the clock information inside the SDP as well. Without this information, a receiver is not able to connect to the stream and decode the packet. So this is why it's important to have a way to allow two devices share the session information. And this is described in what is called the SDP file. AES67 is very clear when defining the attributes to be included in the SDP and the parameter values and their ranges. But again, it is silent on the method to be used to fetch this information. So an encoding device that is basically generating this SDP file must add a way to send this information to its endpoints or to the endpoints that are requesting this information. And we are talking about, again, the discovery of the session, which we understand that is not part of the AES67 standard. So basically, this is it about the session information. An example of the session information is this. These are the attributes, and they are including all the details that a decoder device requires in order to set up the connection and to set up the connection with the stream and to decode the samples. And to set up also the time reference. Now, moving forward, how we made this available onto our devices. As we said at the beginning, Extremer M400, IPFormer, and the new Extremer MPA400 are the devices running IP audio client. And AES67 is the application mode that we added starting from firmware version 2.7. After this firmware, when you update your devices, you will have this drop-down menu that allows you to configure the AES67 mode. What happens when you select this configuration and submit? The device reboots, because AES67 is a dedicated mode of operation. So it's not working into the same standard mode that we are used to see into IP audio client firmware before the version 2.7. So when it reboots, it will offer a new web interface with all the AES67 configuration parameters. Which protocols did Barix included into this AES67 implementation? So in regard the stream discovery, we decided to support SAP, Session Announcement Protocol, that is being used by Dante, as we see. Dante after 2015, where we have the AES67 mode available, remember. And we included also the MDNS DNSSD, or Bonjour, as being used by Ravenna devices. So when we have our IP audio client device sitting in a network with a Dante AES67 compliant and Ravenna, we can automatically discover stream session informations through these protocols. And moving forward, we can see that the rest of the protocols are basically following what the standard mandates. Session information is being retrieved from the SDP. At the moment, IP audio client is working on decoding devices. So we are not generating an SDP, we are fetching the SDP through these discovery protocols. The transport is being done over RTP, using, well, RTP stays on the IP protocol. differentiated services implemented as a mean to identify priority packets. Actually, this is not concerning us as a decoding device, as we are receiving those packets, but it's basically supported. The encoding and streaming, we have the standard definitions that AES67 mandates from 16 and 24. We have a stereo channel on the devices, so up to left and right. Currently, we don't have devices with a more capable number of outputs. So this is the maximum channel count that we support. The packet time is not described in the slide, but it's 1 millisecond is the standard one defined in the AES67. The sampling frequency 48 kilohertz, and the synchronization is done over PTP version 2. When you connect our device with a Ravenna device, you must pay attention, because Ravenna, as we said, has an extended set of features. So when you are connecting a Ravenna device to our IP audio client device, you must make sure that the sampling frequency, for example, is 48 kilohertz, since it supports from 44.1 up to 384. Now, the steps to connect our device to a Dante AV I/O. So this, we are already going into the demo. I have a few slides before moving into the real demonstration, just to have them clearly defined in here. And then I will show you on the user interface how this looks like. First of all, you have to set up your Dante AV I/O to operate in AES67 mode. As I said, Dante offers AES67 compatibility mode after 2015 in a firmware update to the Brooklyn number 2. I don't remember the exact version, but this is it. If we look at the Dante controller, this is what we will see into supported devices. There is an AES67 tab, AES67 config tab, where you can enable AES67. And once you have done this, the second step is to create a new multicast flow, where you can see we have a maximum channel count supported of 8 when in AES67. Once this is done and you configured your multicast flow, this is announced over the session announcement protocol to a well-known multicast address. This is why we have a protocol in place. The session announcement protocol says, you advertise your session information to the address 239.255.255.255. This is the standard address used by SAP and by Dante. On our side, having IP audio client running, we also implement SAP, so we know where to look for this information. But before doing that, we have to configure our switches for quality of service and IGMP snooping for multicast traffic management. I have an example here, but of course, this differs from switch to switch provider. They kind of use the same terminology, but it's always better to check with the switch that you are using. This is MIDI-Link. I have it here on my desk as well. And on MIDI-Link, we have the possibility to set up the quality of service using the SCP values. And you can see we have a table that goes from 1 to 64. These are all the DSCP values. And the ones circled in yellow are the ones used by Dante. So going back to the table that we saw before, I have to say to my switch to prioritize packets with tag 56 for the PTP, 46 for the RTP, and 8 for this proprietary tagging that they are using. All the rest of the traffic will use the 0 by default. The IGMP snooping, on the other hand, is as simple as enabling it. By default, it was already enabled on my D-Link switch. And here I have also the possibility to check, for example, for every multicast address being used, on which ports the switch is forwarding the packets. So I am sure that the switch is not flooding the network. The third step is to configure your IP audio client to operate in AES67 mode. So if you just took it out of the box, by default is running in standard mode. You select AES67 and it will bring you to this. Basically, you do the selection. and it will bring you to the AES67 mode. Once you are in AES67 mode, it reboots. When it will power up the device supporting SAP, will automatically identify the stream. And in the AES67 tab, you have basically the discovery configuration, which these are the default parameters, and the list of streams automatically identified. We can see that the protocol used for the discovery is SAP. The device provided this stream name. This provide automatically from the Dante device. The domain is the default one, is 0 and is not available in the session information. The IP address of the originating device, so this is the IP address of the Dante AVIO, the RTP port being used, and the last activity. We can see that the last activity is just now, so the stream is available and it can be played. In this case, it's already playing because we have the stop button at the end, where we can see that we can stop the stream at any time. If we click on show more related to the SDP column, we have the access to the entire attributes identified in the SDP file. So we can double check what the encoding device is providing. And in our case, these are the SDP information automatically fetched. When the last activity is saying 16 minutes ago, like in this example, this means that the stream is not available since 16 minutes. And you have also the possibility to delete it. So this was basically it. We can now see this applied into live demonstration. Well, it's nothing fancy, but I think it's always better to provide you a visualization of how I do operate on the devices. So let me go back to my... Let me show you first of all the connections I have here. Well, the devices are connected to the D-Link switch. This is my switch, it's a PoE one. And I have the Dante connected to the same switch. Dante AVIO provides me with two inputs, so I have these two left and right connected to an analog source of audio. If I go into the web user interface, this is how the user interface of our IP audio client device looks like. And it is already in AES67 mode in my case. Of course, on top of the AES67 configuration, we still have all the default network parameter configurations where we can change the protocol from HTTP to HTTPS. This is the web interface connection protocol. When I access this page, I basically have the possibility to access it in an encrypted manner using HTTPS. We can say that this client is a DHCP client or assigning a static IP configuration and the corresponding DNS configuration, just like for every networking device. We have the time settings related to the NTP. This is providing the timing information only to the date and time information of the device. It's not related to the PTP, of course. The security settings are the ones that allows me to enable or disable some important functions on the device that I might want the user not being able to access. So for example, disable the reset to defaults, the update or the reboot function. And I can change the password that allows me to enter into the web interface of my device. By default, our devices offer the password on the bottom. So you can see that there is a password label printed here. You can change it in this area. If you are using HTTPS into a private network infrastructure and you want to add some certificates, CA certificates that allows you connections from your browser in a secured way, you can install certificates in this section. And for IPformer, since this is an IPformer device, we have also the output level and speaker settings that allows me to select the speaker impedance and accordingly which kind of automatic power handling I want to use. If it should be PoE optimized when I use, for example, non-PoE plus switches, or maximum power, when I have availability for getting the maximum power out of my switch, PoE. If I have an M400, this is the example, I don't have these amplifier settings, but I have all the rest. So going into the details, this is the AES67 tab. As we noticed already, we have the possibility to configure MDNS discovery to say if it's available or not. And this will basically look for the stream information into a well-known address, which is the 224.0.0.251. And the RTSP is the protocol being used to fetch the SDP file. So the discovery and the fetching protocols. This is what basically Ravenna is implementing on their side. While the session announcement protocol is always active into this multicast address, but if you use, for example, another implementation from an encoding device, not using the standard default address provided by SAP, then you can change it in this field. And in this case, I have my Dante AVIO already connected in the network. It is providing this stream and these informations. I forgot to mention what the period is. The period is the interval at every, so in seconds, every time there is an announcement and advertise of the session information made by the encoder. So in this case, we have the Dante device advertising every 30 seconds this session information. And all the details are described in the SDP content. Now, one important thing I haven't mentioned, but this is actually very important, is that what if you are using an AES67 compliant device that is not supporting any of these discovery protocols? So it's not supporting MDNS, RTSP, and SAP. Well, normally devices AES67 compliant are capable of providing you with the SDP information manually, let me say. So encoders that are giving you the SDP attributes, you have this file basically generated and available somewhere on the encoding side. And what we are providing on our IP audio client is the possibility to add the new stream from here. So you can give the stream a name, and here you paste, sorry, the SDP content that you copied from the encoding side. And this is basically possible as well on our IP audio client. Important to check and mention is the PTP and RTP statistics. PTP domain, by default, this is always 0, which is the standard one defined in the AES67 standard. But if you have systems, devices that are using a different domain, then you can change the domain being used in here. If I am not wrong, I'm not a PTP expert, but I think there are 4 different domains and the custom ones that can be defined in some devices. And you can basically change the parameters to use a different multicast address. The 4 standard ones uses the PTP address that we saw before, 224.0.1.129, if I'm not wrong. If you change to this number to 1, for example, you are saying, okay, don't look for the information on PTP to this multicast address, but use the 224.1.0.130 or .131 or .132, according to the 4 different domains. Then we have the PTP status. We can see that the mode is now slave. Now this term, I think we should change it, is not, let's say, accepted anymore. And I want to put up front, we are not assuming anything using this term in our devices. We will change it probably, because now the right terms to be used are leader and follower, because of this changing in terminologies that we saw. But yeah, you got the idea, right? So slave basically means that we are followers of a PTP reference clock. And at the moment, it's not possible to use our devices as master. So when you connect our IP audio client to an AES67 compliant device, make sure that the other device, at least one device, is capable of providing the PTP master clock. In this case, the Dante is capable of doing that. And this is the grandmaster ID of the PTP originating device. And we can see that the status is locked. So this status changes according to the PTP, if it's locked or not. If this is not locked, it's a problem because you cannot play the audio in a synchronized way. And you can hear a lot of glitches into the decoding process of the decoder. Or you are not even capable of hearing anything. Now, let me play this stream. Once I play the stream, so now I'm playing the source, I have also the RTP statistics and errors. We have the source name, muted no, so the stream is actually playing. The RTP are being received, so receiving RTP packets, yes. We have also a minimum packet arrival time. Well, basically this information is not implemented, is always 0 at the moment, but it will be. And then we have all the errors counters. So we have sequence error, we have stream source errors, the payload type errors, and the packet timestamp errors. So these are all errors related to the analysis of the RTP packets received. Of course, if we have these counters going up a lot, there are problems in my network. So it's important to check if the switch is properly configured, if the quality of service is configured, and if the stream generating device is providing a different, maybe sampling frequency. Everything has to be like aligned. And then we have the usual, let me say, status information about our devices, from the device information, network, system, licenses, and eventually mass storage information if USB keys are connected. The logs, default to reset to default the device, update is where you update the firmware. When we release a new firmware update, here is where you have to upload it, and the reboot. I wanted also to show you how to set up the stream, the multicast flow from the Dante controller. But unfortunately, for some reasons that I still have to investigate, my Dante controller is not working properly. I didn't have the time to investigate a bit further, but you got the point watching the slides that we saw before. It's quite easy. You just need to enable AES67 mode and configure your multicast flow. Once you do that, that will be provided into the SAP information. And if we go again into here, we see that this stream is basically being provided into this RTP address. And one thing I haven't mentioned is that AES67 in the definition of the standard says that the RTP should go into the multicast network 239.x.x.x. So any IP into the 239 network. In fact, we can see that the Dante is using this multicast address. Okay. Now let me go back again into the presentation, and we can see now, to close, AES67 is largely promoted by AIMS, or the Alliance for IP Media Solutions. You can see the key members of this alliance and more key members here. Some are full type of members, some others are associates. These are the associates ones. We can see some big names in this list, and they are basically part of this alliance. A lot of professionals are involved in maintaining the standard, and it is being continuously supported and documented by the Audio Engineering Society. So via AIMS, which is the main promoter. So the maintainer and the supporter are the ones for the from the Audio Engineering Society, and the main promoters are these guys at AIMS, which is an alliance of multiple companies. We are seeing now that AIMS is proposing a roadmap that will converge in seeing this main adoption of IP-based protocols also in the SMPTE standards. And we can see now AEMS is working towards what is now called IPMX, or it is the IP media experience, which is a proposed set of open standards and specifications that enables the carriage, the possibility to move data, audio, video, compressed and uncompressed over IP networks. And this is with the key for the Pro AV market, with the key target for the Pro AV market. So this is including provisions for control, copy protection, and connection management, and security, nonetheless. And the roadmap for this IPMX is visualized in this slide, is available on their website as well. It's nice to see they started from the definition of AES67. So this conglomerate of multiple standard and technologies that will be applied using the same kind of concepts into the SMPTE. In fact, AES67 today is already part of a subset definition of SMPTE ST2110, which is used from the SMPTE guys, which are much bigger than the AES67, because they are the guys for the Society of Motion Picture and Television Engineers. So we will see more and more adoption of AES67 for transporting audio into broadcast environments. Even if it is used also from the other side, since it is compatible now with Dante, for example, the main adopter into the installed sound environment category, let's say, it will be, I think, really, really useful for many vendors, for many, end users that will have the choice to choose not not having to accept the compromises. The consultants doesn't have to accept this compromise anymore. They can choose from different vendors and they will have a future-proof solution that will allow them to exchange a product, not relying on a single supplier. And this is the key of IPMX as well, and of this whole roadmap that you're seeing now on the screen. Barix, as you know, is involved in IP-based audio codecs, in manufacturing IP-based audio codecs since 2001. And let me tell you, we are super happy that this is finally happening. We are seeing mass adoptions of those standards in the industry. And with this, I want to close the presentation and leave some space for the question and answers.